Electronic structure of atoms. Okay, we understand quantum mechanics, well, at this level anyway. Particle wave duality, the fact that the electrons around an atom are wave-like and particle-like, but that forces the energy levels to be quantized. And we saw what the shape of those look like, those waves. They look like S's, P's, D's, and F orbitals, and we know how many orientations there are for each one and how that all kind of fits around in different levels, fits around the nucleus of an atom to actually give you the full atom. So the next question here, now that we understand the basic structure of that, is what is the electronic structure? In other words, when we start putting all of these electrons in there, what are they going to look like? What kind of wave are they going to adopt? Let's say I just take one electron and throw it at a nucleus, all right? What's it going to end up looking like? A 4F? Maybe it looks like a 5-2, or I'm sorry, 5S, or maybe it looks like a 3D, right? So what is it going to look like? And then I take a second electron, I throw it at it. What's that one going to look like? A third one. Now I know from the Pauli exclusion principle that I know no two electrons can have the same four quantum numbers, so no two electrons can have the same size and shape and orientation. Yeah, but still, which ones are they going to assume? The answer is actually pretty easy, and I think it's pretty obvious. The first electron would go to the wave that has the lowest energy. Everything in nature goes to the lowest energy, the most stable. Right? The very lowest energy, and I know the lowest energy is down there in that ground state where you have E1, n equals 1. Okay, so if it goes into the n equals 1 level, I think what kind of waves are down? The s orbitals, that's it. A 1s. Remember, there are no such things as a p. There's no 1p. You have to go up to the second level before you get a p orbital. There's no d's or f's either, right? So we just have the s, and so that first electron is going to look like a 1s orbital. Right? Now what about the spin? Up or down? There's only one orientation, so we don't have to worry about that one either, but there's spin up or down, so I don't know. Those are 50-50. Let's give it an up spin. The second electron, the lowest energy again. Well, it's going to be that 1s again, because then I could do a spin down. That's a different set of quantum numbers. So I'm going to have those two electrons in that 1s orbital. If I put a third electron in, well, now that 1s orbital is all filled up. It's going to have to go up to the next energy level, and whichever the next lowest slot is, that's the shape of that electron, which is going to be a 2s. The question is, what is the order then of these energy levels? I know it goes 1, 2, 3, 4, I know. But remember we talked about before, when you get up to that fourth level and above, they start overlapping a little because you lose that degeneracy and the levels actually start squishing together. And so with the loss of degeneracy and the squishing together, they start to actually overlap a little. And so the order is not quite as straightforward as you might think it is because of that phenomenon. Here is the order of them. And by the way, this idea that the electrons are going to just start filling in from the lowest energy and build up from there, that's called the Aufbau principle. Aufbau from the German word aufbauen, which means to build up or to build upon. So we're just building upon or building up through those energy levels of the different electrons and the waves of them. So what is, again, the order of the energy of these orbitals? Here it is. The 1s is the lowest, and then the 2s, and then the 2p. So far so good, this makes sense to me. And then the 3s and the 3p, so far so good. And then the 3d, no, not the 3d, actually the 4s. Well, that's interesting, right? The 4s is overlapping, I guess, a little bit with that 3d, and when you look at the order, the 4s actually comes first. It's a little bit lower level than the 3d. Okay. Now we go up to the 4p. Well, we already did the 4s. The 4p, that makes sense. 4d, no, not the 4d. It actually goes to the 5s, then back to the 4p, and then back up to the 5p, and then the 6. Okay, this is getting all mixed up because they're overlapping. But that is the order of them. And so if I'm going to start throwing these electrons at this atom and fill them up, that's the order that they're going to fill in. So I have to know that order. Okay. And of course the number of electrons in an s, that can hold two of them. 2s can hold two of them, a 2p that can hold 6 electrons, because there's again 3 orientations, and I can go an upspin and a downspin in each one of them. So that's a grand total of 6, and then 2 more for this 3s, 3p, 6, 4s, 2 of them. Oh, with the 3d, well, there's 5 different ones there, so that's a grand total of 10 electrons that could fit in there before I have to go up to the next energy level, etc., etc. So, electron configuration. This is a notation which tells you exactly what each of the electrons in an atom looks like. In other words, what are the quantum numbers of each atom? Right? What are the shapes of them, the orientations, that kind of idea. So we'll start simple. Carbon. Carbon is number 6. 6 electrons. If I pull the periodic table, here's carbon right there. Again, it's number 6. Actually, I don't have that. I don't have that showing the number. I think I could probably do that though fairly easily. Classic map. What am I trying to look for here? Here we go. Maybe show element. Well, let's see. Element name. Well, there we go. There it's showing up. So carbon is number 6. Just counting through it, which means again 6 protons, 6 electrons. So if I'm going to tell you what the electronic configuration of carbon is, I've got 6 electrons, and I got to tell you where all those 6 electrons are, what level, what is their shape, what's their orientation, and their spin. The electron configuration. So carbon, those 6 electrons, well, I'm going to fill them in the same order as usual. The 1s is the lowest energy level. I can fit 2 electrons in it, an up and a down. So there it is, 1s with 2 electrons. I put it as a superscript. Next one up is the 2s. Put 2 electrons in there. So far I'm up to 4 electrons. I got 2 more to go. So the next one is the 2p. I put 2 electrons in that one, and I'm done. There's all 6 electrons. That's the electron configuration for carbon. 1s2, 2s2, 2p6. I'm sorry, 2p2. I was jumping ahead of myself. 2p6. 6 is the maximum number that a p could hold, right? Because you have the 3 different orientations, 2 per, and so that's a grand total of 6. That's what I was thinking about. But for carbon, no, 1 here, 1 orbital here, 1 orbital here, 2 electrons per, and so that's a grand total of 6 electrons. That's what carbon has. What about bromine? Again, look at the periodic table. I closed it by mistake. There we go. Periodic table, here's bromine, 35. 35 electrons. So I'd have to fill these up with 35. Well, I can get 2 here, and 2, and 6, and 2, and 2, 6, and 2, and 10. I keep on going until I reach 35 total electrons. So 1s2, 2s2, 2p6. Right, 2p6. The next one is the 3s, 3s2. After that, the 3p, so 3p6. And then the 4s2, 3d10. Finally, that brings me up to 30. If I go up here, 5 more electrons in that 4p level brings me up to 35, which again, that's what bromine is, 35 total electrons. So there is the electron configuration for bromine. I'm just filling in these electrons, going from the lowest energy and heading up from there. Keeping in mind how many electrons will fit in each type of subshell. The hard part, I suppose, is knowing and remembering what this order is. You get this this exam question that asks you to make these electron configurations. You're going to have to deal with this order. How can you do that? All right? Well, besides just memorizing it with all these weird kind of overlaps up here, there's actually a very easy way, and that's to think about the periodic table in terms of blocks. All right? So this diagram here, my first 2 columns would be my S block. So again, I pull up my periodic table here. Here's my first 2 columns. That's my S block. They're colored blue in this one. Let me resize this here. All right. Oops, this is the one that I need to resize actually. Oh, that looks better. Okay, so these first 2 are what we call the S block. The main group ones over here, the last 6 columns here, is the P block. The middle 10, the transition metals here, the D block. See yellow's D up here. And these bottom ones down here, that's the F block. Why? Well, because actually as I'm adding these electrons, where do the first 2 go? They go into the 1s. And remember, hydrogen is here, helium's over here. If you think about helium as being over here as far as being in the s block, the first two electrons, one block per electron, if you will. I'm sorry, one square per electron. There they are, 1 and 2. Then the next two would go in the 2s level. So here they are. So they're going into this block as I count through my periodic table. The fifth one would go over here, and that's now in the p block, etc., etc. And so if I was to write the electron configuration for carbon, okay, I would put, again, think of helium as being over here in the s block. I would put 2 electrons here, and then 2 electrons here, and then going over here, number 5 and 6 electrons. Oops, here I am, I'm at carbon. There's my 6 total electrons. Looks like I put a couple in the s block, then another couple in the s block, the second row down, and then over here a couple in the p block. When I add them all up, that's 6 electrons. That gives me the exact order. What do the s's start with, by the way? Well, the s's start with 1s, and then next one is 2s, and the next one is 3s, right, all the way down. And so if you think about here, look at the labeling. Here's my 1s for my first row, my second row is 2s, 3s, 4s, and it's just counting down by the rows for my s block all the way down to the bottom one here, which is 7s. Let's look at the p block here, the green one here. What do p's start with? I don't have a 1p. Remember that only L goes up to n minus 1. I have a 2p. That's the first time I see my p orbitals in the second energy level. And so if this is my p block, my first row will be the 2p row. And then the next one, 3p, 4p, 5p, etc., all the way down. Okay. What do the d's start with? The first time I see a D is in the third level. And so my first row of my D block is the 3D, 4D, 5D, 6D, and the F starts with 4, so 4F and 5F. The whole periodic table can be covered with just the S's, P's, D's, and F's. Remember I mentioned that before, we don't need G's actually. We don't have anything big enough to use a G orbital, and this completely covers everything in the periodic table with just those 4 types of orbitals. Okay. So, if I'm walking my way through the periodic table for carbon, I'm going to count my way through, walk my way. In other words, number 1, number 2, remember, put helium over here, think of it as being here. So 1, 2, 3, 4, 5, 6. Whoop, I'm arrived at carbon, so I would stop at this point. And what I do is I literally write down where do I go at each spot. So here's my first electron, and this is my 1s row of the s block. So 1s, and I put 2 electrons in there. That brings me 1, 2. That brings me up to number 3, which is, right here, lithium, right? This is number 3. This is now the 2s level. So I would write down 2s. I put 1, 2 electrons in it. And now that brings me up to 4, 5. 5 is over here for boron. Hey, I'm not in the 2s anymore, right? Now I'm in the p block. And the first one is the 2p. So I would write down 2p. And let's see, 5, 6. I'm at carbon, so I stop. How many did I put in? 2 of them. 2 electrons in the 2p level. I know that's kind of confusing. Let's do another example to see that again. Bromine. If we walk our way through it, this is what we expect to get. And so let's pull this up here. You know what? I'm going to just bring this down. Let me bring this up more and come back to here with this. All right. For bromine, let's walk our way through. Now, bromine is right here, number 35. So I will start with 1. I put an electron here. I put an electron here. That's the 1s. And so there it is, 1s. I put 2 electrons in there. Now I'm up to number 3. Hey, that's the 2s level. So I write down 2s. I put 2 electrons in there, lithium, beryllium, right? And then I get to boron. Now I'm at the 2p level. All right, so I write down there. So 2s had 2 electrons in here. The 2p, I put 1, 2, 3, 4, 5, 6 electrons in there. Well, that's good because that's exactly what p's do, right? There's 3 different orientations, 2 per orientation, so there you go. I put 6 electrons in it. That brings me up to number 10, neon. Number 11, where's 11 on this chart? It's all the way back here. Sodium is number 11. All right, where am I at now? This is the 3s level. All right, so I write down 3s. I put 2 electrons in there. That's 11 and 12. Now 13, here's 13, back in the p block again, right? And so 13 is the beginning of the 3p level. I write down 3p. I put 1, 2, 3, 4, 5, 6. I still haven't made it to number 35, bromine, right? But I put 6 electrons in that 3p level, so there it is, 3p6. That brings me to argon, number 18. Number 19, back to the s level, with this time the 4s. So right down 4s, I put 2 electrons in there. That brings me to number 20. 21, hey, this is new. Now I'm in the d block, right? So I put down, what is that? The d block starts with number 3, right? So 3d. So that's what I write down next, 3d. All right, 21, put them all in here. I go all the way to number 30. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons in the d block there. And so 3d10, that's number 30. 31 is right here. Whoop, back to the p block. This time it's at the 4p row. So I write down 4p. 1, 2, 3, 4, 5. Oh, there we go. I'm finally at bromine. It took me 5 here. And so 5 electrons in that 4p, and I'm done. Okay. A little strange at first, but I hope you see that all you have to do is follow the numbers through the periodic table and ask yourself, where are they taking me? 1s, 2 electrons, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p. Hey, 5th one over is bromine. That's why I stopped. Once you understand the layout of that periodic table, the idea of the s block, the p block, the d block in the middle, and the f blocks way down below, which we almost never use. Okay. Once you understand that, you can get the electron configuration. You can get the order. You don't have to memorize, hey, which one comes next. The 1s, the 2s, the 2p, the 3s, the 3p. What's the order of those, the energy levels? You don't have to memorize it. Just walk your way through the periodic table, and you've got it. Okay, so let me make that the right size again. Go back to my notes here. Orbital diagrams spell this out and show it very, very clearly. We draw a box for each type of orbital. We put an up and a down electron in each one. We label exactly what the orbital is, so a 1s, and it shows exactly where every electron is. This is an orbital diagram. And here's the example for aluminum. So again, on aluminum, here's aluminum number 13. So I'll have to have 13 electrons that I fill in. I walk my way through it. 1s2, 2s2, 2p6, 3s2, 3p1. Oh, I'm done. So I'm going to end with that 3p1 configuration. Here's the boxes. Again, 1s, the 2s, the 2p, the 3s, the 3p. That's exactly the same order that I know and that I saw as I walked my way through the table. 1s2, there's my 2 electrons. 2s2, they're my 2 electrons. 3p6, they're all filled up. 3s2, there they are. 3p1, I only needed that 1 electron in that 3p level, because again, here's aluminum. It just got into the 3p, just 1 electron, and it got me there. So 1 electron, there it is, I'm done. There's my orbital diagram for aluminum. It shows where every single electron is, what the shape of it is, what the orientation, what the size it is, right? What's the energy level? It's all there. Okay. This is the electron configuration if I was to write it out this way. With the boxes and the arrows, this is an orbital diagram. Both ones would be perfect testing questions. Perfect test questions. Hey, let's try phosphorus, because phosphorus will illustrate for us Hund's rule. Yep, another rule for you. All right, phosphorus, P. Where is that on the periodic table? It's right there, number 15. All right, so let's just think about it really quickly. I'm going to have 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3. 3 electrons, and then I get to phosphorus. So 3p3. There's my electron configuration. And that's what I've got written down here. Well, actually, I didn't write out. Yeah, I have it right here, actually. 1s2, 2s2, 2p6, 3s2, 3p3. Took us 3 electrons. Now, here it is where I filled them in an orbital diagram. 1s2, 2 electrons, 2 electrons, 6 electrons, 3 electrons. They're always paired up. I get to that 3p. I've got 3 boxes. I could coal a total of 6 electrons, but to get to phosphorus, I only needed 3 electrons. And so they are, 1, 2, 3. This right here is Hund's rule. Hund's rule says that it's actually a little more stable to spread the electrons out within that orbital than to start pairing up right away. And so, just do this, change this there. 3 electrons. Let me just erase them. 1, 2, 3. If I was to actually put them in, hey, 1 electron, 2 electrons, 3 electrons. I put 3 electrons in the 3p, but that would be wrong. It's wrong because, look, I've paired these electrons, and Hund's rule recognizes the fact that actually that takes a little too much energy to pair them. It's actually much easier to spread them out first, and then go back and start pairing them. Right? So 3 electrons need to go in here. 1, 2, 3. That's the right way to do it, according to Hund's rule. All right, spread them out, and then see if I had 4 electrons. Well, then I'd come back and put my 4th one right there in a downspin to pair it. Right? But if I can, spread them out and don't pair them. That's Hund's rule. All right, so again, orbital diagram for phosphorus. Here's the electron configuration for phosphorus. I want you to look carefully here. I've got electrons in the 1 level, in the 2 level, right there, and the 3 level, right there and there. Right? Any electron that's in the outermost level is really important, to chemists anyway. Why? Because if I'm going to bring another atom in here, and they're going to make a bond, like a covalent bond or something like that, what electrons are going to touch? What electrons are going to interact? The outermost ones, not the ones on the inside, the ones that are the furthest out there, the outer shell, if you will. Okay? Those play a very special role in chemistry. We call them valence electrons. Valence, right there, V-A-L-E-N-C-E. Valence electrons are anything that's in the highest energy level for that atom. The highest one that has electrons, that is. So in this case, that's for phosphorus, that's the 3rd level. And I got 2 of them in the s orbital, 3 of them in the p, so I guess a grand total of 5 valence electrons. That's what phosphorus has. What about these other ones down here? Those are called core electrons or inner electrons. Okay? Those are the ones that they're not on the outside. They're probably not going to be involved with any kind of bonding. They are the core electrons. Okay. All right. Let's go on a little farther. Condensed abbreviated electron configuration. If this is phosphorus, electron configuration, core electrons in the 1 and the 2, the outermost energy, the 3rd level, those are the valence electrons. These are not important in the sense of bonding. They're not going to interact. They are completely filled up. They completely fill up their orbitals and their shells. Right? And they are closer to the nucleus. We call them the core electrons. They're not as interesting as the valence electrons, not to a chemist. All the action in creating new compounds and making new bonds and breaking them, that's going to involve these valence electrons, these outermost ones. Okay. The core electrons, if you look at this, it goes through 2p6 on the periodic table. Whereas 2p6, here's the 2p, 1, 2, 3, 4, 5, 6. It's this noble gas of neon. And so the condensed electron, or the abbreviated electron configuration, says, you know what, instead of writing out all those core electrons, just say neon. Neon brings you up to 2p6. I know it does because I have a periodic table. There's neon, and it's at the end of the 2p6 level. All right, so I've got all the electrons, 1s2, 2s2, and 2p6. All of them that are kind of wrapped up in the designation of neon in square brackets. Those are my core electrons. And then after neon, that is to say, the outermost, the valence electrons, where are they? Well, back here, if I started with neon, number 10, number 11, hey, that's the 3s2, and then a 3p5, I'm sorry, 3p3, that's a grand total of 5, right? 3p3, there are my valence electrons. And so that's what they will write. Neon core, 3s2, 3p3, these are valence. And it really just kind of gives us a nice condensed way to write that electron configuration where we're talking about the core, not so important, right? But then the valence ones, much more important. There are 5 of them here for phosphorus. When you write the condensed electron configuration like this, you always use one of these noble gases, one of them in that very last column, right? The noble gases to signify your core electrons. So I could put krypton in a square bracket, or helium, or neon. Any of these noble gases work just fine for talking about the core. All right. Figure 630 actually shows you the electron configuration for the outermost electrons, the outer ones, which is almost the same as valence. The definition is actually slightly different. All right, and we'll talk about that in just a hair here. But look at, they're giving you what these are. Like here's carbon. It says 2s2, 2p2. Yeah, well up here I figured out what carbon was, remember? And here it is. Carbon was a 1s2, 2s2, 2p2. So my 1s2, those are my core electrons, and then the outermost, the 2 level here, those are my valence electrons. There are 4 of them here in carbon. And so they're just showing you that outermost level here, carbon, 2s2, 2p2. Right? Same thing with any of these out here. Excuse me. They're just showing you the outermost electrons, those valence electrons. So you can kind of check yourself to see if you're doing it right. The outermost. Exceptions to the filling order here. I got to talk about inner outer valence as well. I guess we'll do that right here. All right. Once in a while, you're going to find a situation where the order of the electrons does not follow what we've already addressed, what we've already explained. There's a little twist, there's a little mix-up. There's not a lot of them, but there are some exceptions. So, I mean, for example, chromium. If you look at this, and here, let me just blow this up a little bit here. If you look at chromium, right there, number 24, chromium, what I would expect the electron configuration to be would be a noble gas argon core, that's number 18, argon, and then I'd have a 4s, 2 electrons here, that's this right here, and then from number 21, 1, 2, 3, 4, 3d with 4 electrons. So 4s2, 3d4, that's what I would expect. And yet look at what it actually is. It's not 4s2, it's 4s1. And it's not 3d4, it's 3d5. Okay, I can see what happened. One of the electrons that was in the 4s2 actually bumped itself up and went up to the 3d and became the 5th one electron there. So 4s1, 3d5 is the correct electron configuration. Look at this below it. Molybdenum does the same thing. 5s1, 4d5 instead of 4d4 is like what you would expect it. Over here, copper does the same thing. I would expect this to be a 4s2 and a 3d9. Instead, it's a 4s1, 3d10. It does the same thing. It kind of robs one from that s level and gives it. Right? What's happening? Well, it turns out that half-filled or totally filled d sublevels are a little more stable than not. And so, if you have 4 electrons like chromium in the 3d level, if I could just get one more electron, it would be half filled. It would be 3d5, and that would be more stable. Where can I get this? Well, the nearest orbital, the nearest meaning energy level, which was the 4s, and so it steals one from the 4s, gives it to the d, just because it wants a half-filled d shell. Same thing with molybdenum. Copper does the same thing, except here it's only one away from being a fully filled d shell, and so it does the same thing. It robs one from the s before it, and therefore gaining a filled d shell. Right? Look at silver, does the same thing. Gold does the same thing. Right? Those half or totally filled d shells are just pretty stable. And so if you're like one electron away, we actually see a little bit of a switch in the order that they're filled in. Okay. And so here's some of those exceptions I was just talking about, chromium and molybdenum, where you think it would be this, we steal one of these s and we give it to the d, so it ends up that. They all do the same thing to chain that half or completely filled d shell. Alright, there are some other exceptions to the order of the filling. Those are the only ones that I want you to worry about, the half and the totally filled d shells right now. Okay. Alright, I said I had to come back to this idea of inner, outer, and valence electrons. Alright, we've already defined 2 of these. We said valence electrons were the ones in the highest energy level. Core electrons, sometimes called inner electrons, are the ones with that noble gas beforehand. They're the inside ones, right? But if you look at something like gold, here it is, gold 6s2, 4f14, 3d9, Actually, gold would become xenon, remember, because it steals that. And once you know it, look at this, I'm finding some more errors in my notes. Let's just go ahead and change these right now. That, whoops, should be a 5s1 and a 6s1 because we stole an electron out of it. And so the same thing here. What I need to do is actually make this a 6s1 and a 5d10. That's the right configuration for gold. All right. Valence electron, well, let's see, the highest energy level here is the 6 one. And there's one electron there, so there's my valence electron. My core is the neon, or I'm sorry, the xenon noble gas. Those are my inner, or my core electrons. Well, that leaves me with these guys, a 4f, 14 electrons, and a 5d, which are not part of the core, but they're not valence because they're not the highest energy level either. Anything beyond the core, so all of these guys out here after the noble gas xenon could be considered and are often called the outer electrons. So in that case, we have inner and outer. Only that highest energy level is considered the valence, and the inner ones sometimes, like I said, are also called core. All right, so if you just kind of remember this, I think, you know, this is the important thing, this guy right here. If you remember inner and outer and valence, you'll be all set. One last thing to talk about in this section, ions. What happens to the electron configuration when you make an ion? You either add an electron to make it negative or remove an electron to make it positive. Right? Well, the negative ones are really easy. It's just like the Aufbau principle. You throw another electron at it, well, where's it going to go? Well, it's going to fill up in the same order that we've been talking about anyway. So here's an example. Oxygen. Oxygen has that configuration. It's a helium 2s2, 2p4. If you give it 2 electrons, remember oxygen likes to be a 2 negative, right? It's in that column where the gain 2 electrons to be like a noble gas. So if you add 2 electrons to make it O2 negative, where are they going to go? Well, there's still room in this p level, right? I only have 4 electrons, so I put them right there. Now it's 6 electrons. I'm done. All right, so making anions, making negative ions, pretty simple. You just add them like you normally would. What about cations, positive ones? For the most part, same idea, except we're removing them. So something like sodium, periodic table, here's sodium. It's going to be a 1s2, 2s2, 2p6, 3s1. And then I'm going to remove 1 electron from the highest energy level, the 3s1. And so here we go, a 3s1 becomes a 3s0. Now it's a positive sodium, and it has the same configuration actually as just the noble gas neon. All right. The one exception you need to worry about and think about is with the transition and the intertransition metals. Remember that overlap we're talking about, and then we got shielding of the nucleus from all these electrons and such, and the order of the energy levels. It turns out that when you remove electrons from transition and intertransition metals, right, they will always come out of the s orbital before they come out of the d or the f orbitals. Transition and intertransition metals, sorry, they overlap a little bit. That's just the way that they are the most stable. So let's look at, for example, iron. Iron on the periodic table, there it is, number 26. That would be a 4s2, well, let's see, it would be argon, and then 4s2 and 3d6. All right, 3d6. That's the electron configuration for normal iron. There it is, 4s2, 3d6. If we want to make an iron 3+, remember iron likes to be either a 2 or 3+ in its charge. So if we make an iron 3+, I have to remove 3 electrons. Where are they going to come out of? Again, if you're a transition metal, don't take it out of that D1 first. Take it out of the S just before it. So I'm going to lose those 2 electrons. That'll become a 4s0 like this. But I got to take 3 out. So once I remove those, now I can come back and remove that. So the 3d6 drops down to a 3d5. So there you go. There's the electron configuration of iron 3+. 4s0, 3d5 is the correct answer.